All right, so this is a paper so this is a paper from this year called C5 Cloned Concurrency Control that always keeps up. And the background of the paper is going to be very familiar to most of us. It's about asynchronous replication. So it means that you can do writes on the primary and the backups will replicate the writes eventually. So in systems like this, the primary receives writes and the primary's copy of the data, it reflects some order of operations. You can have multiple concurrent writes, but there's some final sequence. And this paper seems to be talking about serializability. They don't say that, but all of their examples are kind of about the serializability isolation level, which means that every transaction seems to commit atomically at one instant. So that means that when you read from the primary, you'll always see the data reflecting some serial order of committed transactions. So the primary ships logs to the backup, in reality, at least two backups. And the backup replays the primary's log, and clients can also read from the backup. The backup implements something that this paper is called cloned concurrency control, which means that the client reads always see monotonic prefix consistency. That means they see the version of the data progressing forward, that's monotonic, and it has prefix consistency, meaning that it always reflects all of the operations up to some specific entry in the log. So this describes not just C5, but all primary backup replication systems. Now, the problem with these systems is that usually there's higher parallelism possible on the primary versus low parallelism on the backup. So if the backup, for example, if it were single-threaded, if it just read log entries from the primary and executes them one at a time, it probably won't be able to keep up with the primary's peak throughput. So the backup will fall an arbitrary amount behind. This will risk data loss if the primary goes down before its most recent writes have been replicated anywhere. It means that reads from the backup can be very stale. And an incident which we've seen quite often at MongoDB and which the paper also mentions at GitLab is that a backup can just fall off the end of the log. So the system only stores a finite amount of log. There might be a sort of an output buffer on the primary and an input buffer on the backups, but that's of finite size. So if they're storing like 1 hour of log and all the backups are more than an hour behind, then they are permanently unable to catch up because they are missing entries that they need to replay next. And then you have to manually restore them somehow from like a snapshot of the primary or something.
Jesse, can you help me here? High parallelism on the primary versus low parallelism on the backup. I'm not sure I quite buy it. Like backup's job is easier. It's just replicate stuff, and high parallelism sometimes could be of due to detriment of getting things done. I mean, the backup is just copying things, whereas yeah, primary is doing more things, but doing concurrently sometimes is even slows things down. I mean, can you maybe first explain in the simple ideal case why this is true, like high parallelism on the primary improves things, and secondly, does the paper give some real justification on this from database? I'm not quite sure I buy this actually.
That's a really good point. Let's hold that until the end,
Okay.
because I think that's really worth talking about.
I mean, I'll try. It's hard, but I'll try.
You try to remember?
No, I'll try to hold it till the end.
Okay, all right. So we'll talk about that at the end. This paper asserts that low parallelism on the backup is a problem. But they are in conflict with another problem that they're also trying to solve, which is that unconstrained parallelism on the backup would allow consistency violations. And I'll show an example of this, but we can go fast because this is really familiar territory. So let's say that there's a primary write. We've got transactions T and U running concurrently, and they're both writing to rows X and Y. They could execute in any order. It happens that T gets the lock first and writes to X, and then it writes to Y. U writes to X and then Y. The outcome is that X and Y both have U's value. So client C U's write to X and Y. The primary is implementing some kind of concurrency control. The paper can abstract that away, although we do seem to be talking about serializability, so it would appear that first T commits and then U commits, and each of those is atomic. Great. What about the backup? So if the backup had unconstrained parallelism and it was allowed to replicate these in any order, then it could end up violating the isolation or consistency guarantees of the primary. So we've got T and U writing to X and Y. T writes to X, and then we start interleaving writes differently on the backup from on the primary. So now U writes to X, U writes to Y, and then T writes to Y. So we end up now with inconsistent reads. A backup would see U's write to X, but T's write to Y, which is impossible in any serial transaction order. It doesn't match the primary, so this is a violation. So, all right, all of that was background. Now we get to supposedly novel stuff in the paper. So the C5 backup algorithm is what executes on the backup, and it has the same degree of parallelism as on the primary, while guaranteeing monotonic prefix consistency. So it's supposed to be the best of both worlds. The backup receives a log of writes from the primary in the order that the primary executed them. Time goes right to left, so the oldest write that was executed first is on the right. Now, the backup has a separate queue per row. So X has a queue of writes and Y has a queue of writes that need to be replicated. And the backup moves log entries in order from the primary log into its per row queues. And again, the first write is on the right. So what do we do with these queues? We also have a scheduler queue, and it's got pointers to the per row queues. And it's set up so that the earlier writes, like X was written to first on the primary, so it gets the top location in the scheduler queue. And let's say that the backup has a thread pool with 2 workers, and these workers can execute writes in parallel. So one of the workers grabs the head of the scheduler queue and follows that pointer to the queue for X. And the other one follows the next pointer to the queue for Y. And they can start executing in parallel. If a worker finishes the write to X first, then it can do the next write to X and the same for Y. If they conflict, actually they won't conflict, right? Because they're doing, they're each sticking to their per row queue. As soon as a write to X is complete, it's safe to write the next write to X, and the same for Y. So this schedule ensures that each row is written to in the same order as the primary, but you could still see inconsistencies if you read from the backup, because one of the workers might finish writing to Y before X or vice versa, and you would see a non-serializable view of the data temporarily on the secondary. So how do we ensure that whatever guarantee the primary is making about isolation, we also see that on the secondary? So this is the other half of the snapshot of the C5 algorithm, which is its snapshotter. We just finished the scheduler, now we're on the snapshotter. This is a diagram from the paper. So on the left in green is the current snapshot, and that is completely written. So you can read from it with read-only transactions, and you'll see a prefix consistent view. Here's the primary log. It's being replayed on the backup, and I apologize that it's now the opposite direction, so the oldest entries are on the left now. So we're replicating from left to right. So we choose two entry IDs. We call them C and N. And everything in that span, that will become the next snapshot in yellow. So log entries between C and N are written to next in yellow, and log entries after N are written to future in red. As soon as all the writes in the yellow next snapshot are complete, then we can shift everything to the right. So the next will become current, future will become next, C and N shift to the right, and the cycle repeats. I think that you could just do this with 2 snapshots instead of 3. I think that the problem they're trying to solve with 3 snapshots is that installing a snapshot might take time, and they don't want to block reads while they're installing the snapshot. So they want to be able to, or actually they don't want to block replication. So they want to be able to install next as current while they're still writing to future, and then install future as next, again, without blocking writes. So I think that the reason why they need 3 instead of the more intuitive 2 is to avoid blocking replication while they're swapping snapshots. So that's the whole thing, I think. That's all of C5. It's got a scheduler, which allows a lot of parallelism without writing to individual rows out of order, and that it's got the snapshotting thing to allow consistent reads from backups. Their goals were to match the primary's parallelism on the backup, which they call cloned concurrency control that has commensurate constraints. So that's why it's C5. And they also want to preserve monotonic prefix consistency on the backups. And I think we can see that it's like plausible. There is a sketch of a proof, but there is no actual proof, but it all looks plausible to me. They've also got a fair amount of implementation at the back end of the paper with charts about performance. And so to start to answer Murat's question, it does seem like their system, which is a variant of RocksDB, the backups fall behind with their old replication protocol. And then when they implemented this, the backups were able to keep up. So at least in that very specific circumstance, but I don't actually remember what, how parallel the previous algorithm was. I need to go back and look at that. Like, how bad was their backup parallelism before they implemented this? But I think that's all fairly specific to RocksDB, which is why I'm skipping over it. I think if you're an implementer of another system, what I covered here is the meat of it. So these were their goals. My evaluation of the paper is that matching the primary's parallelism on the backup is good, although let's talk about that. Maybe I'm wrong. I do think that this is not novel. And I know it's like sort of a bit of a jerk move to attack a paper for not being novel, but they really thought that they were doing something new, and I'm really pretty sure that they weren't. Here's a change to MongoDB that's more than 6 years old now. At the time, we had just implemented document level locking, so we got rid of the database level lock. And so Elliot noticed that we could increase replication parallelism. So we wrote secondaries should stripe writes by doc if doc locking is on. The previous unchanged code had hashed the namespace NS, which is the name of the collection, and then used that to determine which writer vector, so these are per thread queues, to push onto. So this was collection level concurrency before this change. There are 16 threads that are pulling out of these vectors. And then after that, he checks if document level locking is enabled. And this is a CRUD operation, so it's not like some reconfiguration or something. If it's just a insert or update or delete, then combine the document ID with the hash of the namespace and use that to decide which thread to schedule it on. So I'm pretty sure that this is the C5 scheduler algorithm, but it's 6 years ago. And we also did snapshotting, so you can read from a consistent snapshot. But we only needed 2 snapshots because for us, you can just read at a timestamp and you don't have to spend time swapping snapshots around. So we didn't need that 3rd snapshot. This was released in MongoDB 3. So I don't know how novel this is. Also, parallelism isn't the only cause of replication lag. Obviously, you can just have a slow network between the primary and the secondary, especially if you're geo-distributed. The secondary is simply unable to pull messages from the primary fast enough. MongoDB implemented compression over the net, which helped a lot with that. We are still struggling with a problem where the primary is just so overloaded that it's unable to send log messages to the secondaries. The threads on the primary responsible for that get starved. So we need we may need to overhaul our scheduler in order to fix that. And then you could also just have a misconfigured system where the secondaries don't have as much CPU or memory or whatever as the primary, but nobody can really solve that. That's user error. So I think that calling this C5 bounded replication lag, it's assuming that parallelism is the only problem, and that's obviously not true. But the paper's well explained. It's got nice diagrams. And so if there are any systems that haven't already implemented C5 because they didn't notice this optimization, then this paper would be helpful. That's that. So is more parallelism on the backup better? I think for Mongo, well, yeah, I'm not sure. We implemented up to 16 threads writing on the backups, and I think that that's good enough for MongoDB. There could be more parallelism on the primary, but the backup, not having enough worker threads has not been a cause of lag for us.
So we assume single core, not multi-core, and then do we assume one disk versus not many disks?
Oh, interesting. I think that we assume multi-core, that the threads are truly parallel.
Oh, okay.
On the primaries and the backups. That's a great question about disks, because everybody might just bottleneck on the disk.
Yeah, that was one of the kind of assumptions they made in the paper, right? The I/O is no longer the bottleneck. Yeah, so